Today we're going to talk about atomic theory and the molecular and atomic structures that underlie atomic theory. We're also going to talk about Dalton's law as well as how to calculate the actual atomic mass of any particular element. Matter, as we've talked about actually in the last lecture, is composed of very small particles called atoms. Now, the term atom was actually coined by a Greek scientist and means, or comes from a Greek word which means indivisible. And it was thought that the atoms were the foundational particles and that there was nothing smaller, or atoms were not made up of anything smaller than themselves. However, as we'll see in just a few minutes, this turned out not to be true. An element is defined by the fact that it only consists of one atom, or one type of atom, and has a uniform mass for all the atoms within that element. And what you see here is a penny, which presumably is made of copper, and it is entirely made up of copper atoms. Atoms of one element differ from atoms of all other elements in virtually every way that you can imagine, including size, weight, and chemical characteristics. On the other hand, molecules make up what we call a compound. And a compound consists of atoms of two or more elements combined in small but whole number ratios. Now that's an important concept to keep in mind. The atoms are combined together in a whole number ratio, such as 2 to 1, 3 to 1, 4 to 1, 3 to 2. And these ratios are small, not large. And a given compound, the number of atoms of each element always presents in the same ratio. This is called the law of definite proportion, or the law of constant composition. So for example here, you have what's called iron 2 oxide. Iron 2 oxide is made of one copper atom and one oxygen atom, and so the proportion in this case is 1 to 1. And whenever, no matter where you find the iron or copper 2 oxide, it will always be a 1 to 1 proportion. So here you have two elements together, copper and oxygen, and then you have combined together as copper 2 oxide. Atoms cannot be created or destroyed, and that's part of the law of conservation of mass. But when a chemical change occurs, the atoms are rearranged in such a way that they still represent the same mass, but are different in terms of the way they're combined together. And you can see on the left here, you have copper atoms all associated with each other. And in the atmosphere are oxygen atoms all associated with each other. But when they combine, you see that there's one oxygen atom for each copper atom, and they're all combined together. So, for example, let's ask a question about this example right here. Take a look at this diagram and answer this question. Does the following chemical change represented by these symbols violate any of the ideas of Dalton's atomic theory? Now you can stop the video for just a second and think of your answer. The answer is yes. The product consists of only one green sphere and one purple sphere. This violates Dalton's postulate that atoms are neither created or destroyed, because you have two green and two purple on one side and only one of each on the other side. So you would have to multiply the right side by 2 in order to keep the atoms consistent and not created or destroyed. And how about this one? Again, you can stop the video and think about it. In this case, the answer is no. This does not violate any of Dalton's postulates. Atoms are neither created nor destroyed, but are redistributed in small whole number ratios. You can see that there are 2 purple on one side and 2 purple on the other side, 2 purple on the left, 2 purple on the right of the arrow. You see there are 4 green on the left of the arrow and 4 green on the right of the arrow. The arrow represents the difference between the starting materials, that is the reactants, and the ending materials, or the products. The whole number ratio here is 2 to 1 green to purple. So again, a small whole number ratio. Now there's another way of saying this, and that's the law of definite proportions. This is an experiment to illustrate the law of definite proportions. You start out with 10 grams of lead, add 1.55 grams of sulfur, and you make lead sulfide. When you weigh the lead sulfide that you have made, you find that you have exactly 11.55 grams. You take the same 10 grams of lead and now combine 3 grams of sulfur. What happens? You have the same 11.55 grams of lead sulfide, but now you have leftover sulfur. You take more lead, combine it with the original amount of sulfur, you make the same amount of lead sulfide, but now you have leftover lead. What this tells you is that the proportion of lead to sulfur in lead sulfide is always the same, because adding more of one or the other, lead or sulfur, does not change how much lead sulfide you get out at the end. This experiment shows that there's a constant proportion of lead to sulfur in lead sulfide, and adding more sulfur, as in line 2, or more lead, as in line 3, cannot change that proportion. And what you have instead is leftover sulfur or leftover lead. Here's another example. A different way of presenting it. You have a compound, 31 grams of hydrogen or water. This consists of 3.469 grams of hydrogen and 27.53 grams of oxygen. So in 31 grams of hydrogen or of water, you have these proportions of hydrogen and oxygen. Thus, you're left with 11.19% hydrogen, which is 3.469 divided by the total 31 times 100, and 88.81% oxygen, or 27.53 grams of oxygen divided by 31 times 100. If you take a smaller amount of water, it has the same percentage ratio. This again is the law of definite proportion. No matter how much water you have, the percentage of hydrogen in the water and the percentage of oxygen in the water is always, by mass, is always the same. And you'll notice that the ratio is always 2 hydrogen atoms for every 1 oxygen atom. Now obviously oxygen atoms must have a far larger mass than the hydrogen atoms, and thus that's why the percentages here are like 8, almost 9 to 1 by mass in favor of the oxygen, whereas you have 2 hydrogens and 1 oxygen, or 2 to 1 by type in water. Now the law of multiple proportions says that when 2 elements react to form more than one compound, a fixed mass of one element will react with masses of the other element in, again, whole number ratios, small whole number ratios. And that's actually what we showed a couple of slides ago with the lead and the sulfide. If you look at both A and B, you'll find that the copper, which is brown, and the chlorine, which is green, in the B, there are twice as many chlorine as there are copper. In the A, there's 1-to-1 chlorine to copper. So there are actually two different types of copper chloride. One copper chloride is 1-to-1, one copper chloride is 2-to-1. And we'll discuss in future lectures how this occurs. Now let's talk for a second about the subatomic particles. Now, as I told you, the Greeks didn't understand that there were actually subatomic particles. They thought that atoms were the smallest thing that there was. But this fellow here, whose name was Thomson, decided to use something called a cathode ray tube, which generates high voltage electrons, which he didn't at the time know that they were electrons, but that's what this produced. And he used this tube to show that electrons existed. This is the early cathode tube that was invented in 1897, and the experiment shown here fires a beam which is deflected by a magnetic field. And this beam, which is deflected by a magnetic field, was shown to be what he called electrons. The electron is a negatively charged particle in the atom that has almost no mass. Millikan did an experiment to measure the charge of individual oil droplets. The tabulated data is shown on the right here, and what he showed was that the simplest and smallest droplet had a charge of 1.6 times 10 to the minus 19 coulombs, and therefore he postulated that the fundamental charge of an individual electron is 1.6 times 10 to the minus 19, and these other larger droplets are merely multiples of the simplest charge. Thomson then developed a theory or a model of how the atom is put together. A model is a hypothesized theory, or a drawing, if you will, of something that you cannot see even with various instruments. He developed what's called the plum pudding model, shown on the right, or excuse me, on the left. The plum pudding model, he called it that because it looks like, or his thought was, like the English dessert plum pudding, where the positive moist cake, it has embedded raisins or plums, which represent the negatively charged electrons. Later, the later model was called the planetary model, and the planetary model postulated that the center of the atom was positively charged and the outside was negatively charged, like the rings around Saturn. Rutherford did a series of experiments looking at alpha particles fired at a piece of gold film. The gold film here is shown on the right. The source of the alpha particles was radium, and what, to his surprise, occurred is most alpha particles passed through the gold film without being deflected, but every once in a while they would be reflected or bounced in various directions. So what he concluded was that the volume occupied by an atom has to consist largely of empty space, because most of the alpha particles pass through the atoms without colliding with anything. However, there must be something small, relatively heavy, and positively charged that is causing the deflections, and this was termed the nucleus of the atom. This shows the experiment in a little bit higher degree, how most of the alpha particles, shown on the right, pass through the gold foil without striking the nucleus. But you can see that a few will strike the nucleus and be deflected in various directions. So in the center of the nucleus, he proposed something positively charged, which he called a proton. Also in the nucleus, discovered by a different experimenter, was an uncharged subatomic particle, which had the same mass as a proton but did not have a charge, and these were called neutrons. An isotope is an element of an atom which has the same number of protons, therefore it has the same chemical characteristics, and it's called by the same name, such as iron or oxygen or whatever. However, it has a different mass because it has different numbers of neutrons. And so you'll hear people talk about iodine 131 or iodine 129. What that means is that both those iodines have the same atomic number of protons, but different numbers of neutrons. We're going to stop at this point and continue our discussion on part 2.